Tucked away high in the Kuti-Yangtze sub-watershed of the Indian Himalayas, at an elevation of 4,290 meters, sits Parvati Sarovar. According to ancient Hindu mythology, this highly isolated glacial lake served as the sacred bathing place of the goddess Parvati. Pilgrims who make the demanding trek to its shores believe these high-altitude waters possess divine properties capable of healing both the mind and the body. Standing on the bank, that belief makes sense. The water is odorless, exceptionally clear, and takes on a striking turquoise hue. But a recent scientific audit found a reality that strictly contradicts the pristine appearance. The water is categorized as biologically hazardous. Extreme geographic isolation and deep cultural reverence offer absolutely no guarantee of microscopic biological safety. In September of 2023, researchers conducted the first thorough baseline ecosystem study of Parvati Sarovar. The team executed a rigorous field study, testing 14 distinct physicochemical and biological parameters of water. Since we already know the water failed the safety test, we can use this audit as a reverse engineering exercise to isolate the exact anomaly. We need to systematically break down the raw data tables produced by the field researchers to see where the failure occurs. This data-driven approach is the only accurate way to evaluate a high-altitude lake, or HAL. Ultimately, macroscopic visual purity is an illusion. The actual health of the water must be verified through microscopic data analysis. We will start with the physical audit, which establishes the lake's baseline environmental state. Looking closely at this data table from the study, we see the surface water is a frigid 5.56 degrees Celsius, with color units below 5 and a turbidity score below 1. Turbidity is measured in nephelometric turbidity units, or NTU, the standard scientific measure for suspended particulate matter in a fluid column. High NTU scatters light. Low NTU lets light pass straight through. Parvati Sarovar score of less than 1 NTU indicates near-zero physical contaminants. The physical metrics perfectly validate what the human eye perceives. The water is structurally free of physical debris. Next, we examine the dissolved chemical profile of the water, elements that are completely invisible to the naked eye. This table shows the lake's chemical makeup. The pH comes in at 6.4, meaning the water is slightly acidic, but well within safe limits for human consumption. The researchers also detected specific levels of calcium and magnesium. This mineral profile categorizes the lake as having chemically hard water. The measured hardness is 148 milligrams per liter. The permissible limit for drinking water in India is 200 milligrams per liter, so it safely passes. This chart plots total dissolved solids, or TDS, the baseline metric for chemical potability. Parvati Sarovar registers a TDS of 175 milligrams per liter. As illustrated, this sits safely below the World Health Organization's maximum of 300 and the Indian standard of 500. Even trace elements like iron, nitrate, and sulfate were detected in small, manageable concentrations. None exceeded safe parameters. Neither physical particulate matter nor dissolved chemical solids are responsible for the lake's unsafe classification. That leaves the third and final testing category of the study, the microbiological assays. Looking at Table 5, we finally find the critical failure point in the audit. The water contains definitive colonies of coliform bacteria. Specifically, the samples show 62 total coliforms and 9 fecal coliforms per 100 milliliters of water. Fecal coliforms are obligate indicators of mammalian gastrointestinal waste. Their presence means feces are actively entering the water column. Any confirmed count of fecal coliforms instantly disqualifies a water source from human consumption standards. This is the core limnological paradox. Water that is perfectly balanced chemically and physically can simultaneously harbor invisible, dangerous biological payloads. So how exactly does mammalian waste enter an isolated alpine lake with zero sewage infrastructure? It comes down to Parvati Sarovar's specific geological structure. It is a tarn, a shallow depression carved out by ancient glacial activity. Unlike lower-altitude lakes, tarns do not benefit from deep, slow-filtering groundwater aquifers. They are exclusively fed by localized surface runoff. Snowmelt and direct precipitation drain rapidly down the steep, shallow basin walls and straight into the lake. Researchers observed a crucial external biological variable in the immediate vicinity: heavy overgrazing by local herds. These animals deposit raw fecal matter directly onto the thin, rocky, overgrazed topsoil surrounding the basin. When it rains or seasonal snow melts, that surface runoff acts as a direct conveyor belt, washing waste across the rocks and into the water. The specific topography of a tarn makes it a highly efficient, unfiltered catchment basin for any immediate shoreline contamination. Agricultural inputs are only part of the issue. We also must look at direct anthropogenic pressures. Despite its remote location, the lake attracts a steady demographic of pilgrims drawn to its mythology. Desealed's study documented physical evidence of this human presence, specifically the minor littering of plastics and discarded religious garments left on the banks. This pilgrim littering operates on the exact same unfiltered runoff vector as the grazing waste. This exposes a broader reality for all high-altitude lakes. Their unique hydrology makes them exceptionally vulnerable to even minor shoreline disturbances. In these environments, the lack of deep soil means there is zero buffer zone between human activity and the water column. In a closed tarn system, any localized activity on the immediate shoreline directly and instantly dictates the health of the entire water body. This dashboard summarizes the complete, contradictory limnological profile of Parvati Sarovar that we have just deconstructed. Extreme aesthetic clarity and optimal chemical balance effectively mask severe biological hazards. As tourism and pilgrimage numbers predictably increase in the Adi Kailash region, these anthropogenic pressures multiply. This creates an urgent need for targeted conservation and management efforts from local authorities to strictly control shoreline land use. True preservation of these sacred waters requires understanding and respecting their invisible, fragile limnology, rather than just admiring their visible purity.